I don't like it just because of the name, like just because of the exchange, but it's just in reality how it works.
Okay, hi everyone. We'll get started with lecture for today. So if everyone kind of, Okay, so welcome to Python DeCal week 14. So first for some announcements. Final project presentations start in just a week. So everyone make sure you're finishing those up, get any animations or plots you want to share made. So how the final presentations are going to work, they'll be on Monday and Wednesday. Each group will have 10 minutes to present. So we want to leave time for questions at the end, about 3 minutes for questions. So try to make your presentations like 7 minutes long. And make sure that everyone in the group speaks at some point. You don't have to divide it exactly equally, but just make sure that everyone is presenting something. And then for the slides, just have some brief background. You don't need to go too detailed on your topic. The general process, what you guys actually did, and then share your final results. And also apply to be an intern for next semester. So this semester we have 3 great interns. They help out with teaching lectures, as well as grading homeworks and answering questions. And then kind of going into the pipeline of eventually becoming an instructor. So we'll release more details on that, but keep an eye out for that. James, did you want to say? Yes, okay. Yes, there's an announcement on B courses, so you can fill out that form to apply to be an intern. Definitely encourage everyone to try it out. It's really fun just to teach. And decals, are a less stressful way to just teach and learn Python again and help other people. And then we're going to take a class photo on Wednesday. So everyone, if you can, please come in person. We're just going to go outside and take a group photo, and it's just a really fun way to end the course. And we'll also have time for everyone to work on projects. So if you have any final questions you want to ask the instructors, this is also a great time to come in, work on your presentations, and work on your projects. Does anyone have any questions about the last 2 weeks logistics? Yes.
So presentations are going to be Monday and Wednesday next week?
Yeah, so we're going to let people volunteer for if they want to present first, but otherwise it'll just be random order. So everyone should be prepared to present on Monday. Yeah, and we'll have everyone turn in their stuff right before Monday lecture so that it's fair to everyone and that everyone has the same amount of time to work on it. But we just can't fit everyone's presentations on one day.
Also, that being said, if there's some outside circumstance, whatever it is, that means you can only present on one day, or your team can't make it to one day, let us know ASAP.
Yeah, and if anyone in the group has to be on Zoom or something, they can't come in person, also let us know and we can make sure we set that up as well. Okay, so now getting into today's lecture. Yes, another question.
Also after that, then it's that week and then final, so there's nothing, right?
Right, so our last class will be Wednesday, and it'll be the last day of presentations as well, and then you guys are all done with the course. Nothing left from us going into dead week or finals. Yeah, so let's get into today's topic. Okay, so we're going to be talking about machine learning. So as you've probably already seen from trying to do your final projects and getting things more lifelike and realistic, programming real-life applications is really hard. So it's really easy if you want to just do a simple spring, it's really ideal. But once you get into more realistic things of damping, friction, a lot of other things in the system, it's really hard to actually code this and define a model for it. There's just too many things to account for. So the main idea behind machine learning is instead of us explicitly coding up F equals ma and the exact laws for gravity, etc., what if we just gave the computer a bunch of examples so if this is our input and this is the ending, what kind of relations exist there? And so basically letting the computer see the input and the output and then define the rules itself. And so through this process, the computer will basically learn through a lot of examples and experience, as well as some sort of positive or negative weights associated with them. And so machine learning is actually already in a lot of real life applications that you guys use on a daily basis. So for example, with self-driving cars, a lot of the detecting, like, is this a person, is this another car, comes from training on a lot of past footage and, you know, labeling, like, this is a person. And once the machine kind of sees this a few thousand times, it can finally learn on a new example. And then there's also like Netflix and TikTok recommendations. So they basically learn through all of your scrolls and all of your pauses what you like and dislike. And this is just another example of you being the data that the machine is training on. It's basically training on everything that you do on TikTok. And then there's also more on the natural language processing domain, so Siri and Alexa speech recognition. It's not like someone coded exactly how should you pronounce these words, every single word. A lot of it is just using other data to learn. Similarly with Google Translate, and even stuff in the medical field, like diagnosing like x-rays and stuff like that, that's also kind of ties back to the computer vision topics we talked about last week, but that's similarly just processing a lot of images, you labeling a few thousand, and then from then on, the machine can do the rest. And then later today, we'll see an example about face recognition and face tracking. So this is another domain where machine learning is used. Okay, and then looking at machine learning. So there's two main branches of machine learning. There's supervised learning, and this is basically, this also divides more into classification and regression. And so basically you develop a model with laws based on some input data that you're given and output data. So just like fitting a line is an example of supervised learning and regression. You give it a bunch of X values, you give it a bunch of Y values, and then it'll return you the slope and the slope that you can use for your line. And then on the other hand, the main difference with unsupervised learning is that you're only giving it input data. So you don't necessarily know what the outputs will be for the data you're giving it, but then you then trust the computer to go and find some trends among it and group the data further. Okay, yeah, so with supervised machine learning, the main example we've seen so far is regression. So everything we've done with linear regression and using SciPy curve fit, these are all examples of supervised machine learning. And so we've all technically used machine learning already. So that's pretty cool. And then classification is kind of more self-explanatory. So it's an example of just the computer being given lots of images that are labeled, like this is a person, this is not a person. And then from there, it can classify another image. Is this image a person or a car? And then for unsupervised, an example of like class clustering is when Netflix takes a bunch of movies with similar genres, and then it can then classify movies as really random categories, as like irreverent thrillers. So it's not like someone at Netflix came up with this really random category. The machine kind of saw like a lot of similarities and then created these groups on its own, which is why sometimes they're really random categories, if you've noticed. Yeah, so going deeper onto regression. So there's a lot of different types like linear, polynomial, and logistic regression. And how it actually works is that it'll calculate parameters. So in your line, your parameters would be M and B, like your slope and your y-intercept. And it'll basically just calculate the loss. So the error between the point you give it and its predicted point based off the line it makes. And it'll return the parameters that minimize the loss the most. And it's also important to note that real data is never perfect, and there'll always be some error or noise associated with your model. It's just about minimizing the loss and finding the parameters that seem the best. And so for this, it's also really important to consider simplicity versus overfitting. So if you're just given a lot of data points and you don't know if it's necessarily linear or polynomial, it's important to actually plot your data, take a look at it. Because for example, with the same data, these three graphs all have different models, but you can kind of tell that although this plot on the right has the lowest loss, it's overfitting to the data, and if we were to add a bunch of new data points, it wouldn't really predict them well. So it's important that you don't overfit your model too much and give it too many degrees of freedom so that it goes through literally every single point and says, look, it's like there's no error anywhere. And so you can tell that the middle plot is probably the best fit. And this is a bit subjective as well, although there are a lot of techniques to look at like the residuals to make sure they're like random and stuff. But yeah, so this is an important process in the regression pipeline, just choosing the correct model. Okay, so a lot of a main practice that's used when you're actually using data is to split your data into a training set and a test set. And so the training set is to actually train the model, and the test set is to kind of also by its name test the model. You basically want to use the test set after you finish training your model and you think it's working really well, and then you test it on this part of your data that your model has never seen before. And in this way, you can evaluate the accuracy of the model and try to get an accurate judgment of how well will it do on data it's never seen before. So I think one of the most common analogies is that like the training set is your past like homeworks and stuff that you're studying off of. And then your test set is the practice midterm before you actually go off into the real world and like take an actual midterm or final. It's just an intermediate step to make sure that your model is doing just as well on the training data as it is on new data it's never seen before. And so that's why it's really important that you do this split and that you don't mix your test data with your training data, because then your model will just try to overfit to your test data as well and like go through every point and like minimize the error there as well. Yeah, so in general, it's really important to have a high test accuracy, and then having a high training accuracy is more arbitrary since that may mean your model is just overfit. Okay, and then going back to classification. So through this process, you're given many data points with different class labels, and then you then want to predict and classify new data points. So through mainly how you do this is that given your data with labels, you would define some sort of decision boundary, which you can then say, okay, everything to the left of the decision boundary is blue, and everything to the right of the decision boundary is red. And so you can see here, if we have this new yellow point, we could then classify it as red, which seems correct to like our eyes as well. And so kind of going back to what we were talking about before with like overfitting, you can similarly overfit even with classification. So you can see that here, a lot of decision boundaries were drawn, but some are really specific, so they only have like one blue point. And you can tell that even if a new point was placed like right here, it'll probably have a higher chance of being orange than blue. So it's also important that with classification that you're not overcomplicating your decision boundaries and the amount of freedom your model has as well. So you can see here, the classification on the right also seems more general and will do well on future data. Okay, and then getting into kind of the more nitty-gritty of a lot of machine learning. So a big topic is neural networks, which are kind of like a big buzzword in like CS stuff nowadays. But basically the idea here is that you use layers of linear and nonlinear functions to model another function. Yeah, and then each layer will have a lot of interconnected nodes, so it kind of looks like a large network. And then the final weights may not really have any physical meaning, like say, if you're graphing like Hooke's law, the spring force, you could tell that the slope is like the spring constant. But here, since there's so many weights and they're all interconnected kind of randomly, there's not as much physical meaning here. But they're really good at approximating whatever input you're giving them. And so these can get really complicated. You can have like a bunch of different channels, a bunch of different layers. Yeah, but these are actually very, very accurate, kind of scarily so. And you're basically just giving them a lot of data. It's going through all these different layers and adjusting weights, and you can have really high precise results. Okay, and then tying back to astronomy. So machine learning is really important in astronomy as well these days. So some examples are inferring like stellar parameters from spectra. So you can fit some model to some spectra you have. For example, even in radio astronomy lab that you might take when you get to upper division astro classes, we fit like Gaussian profiles and then find like the velocity of hydrogen clouds, stuff like that. Also detecting supernova, that's like classification. So you can take a bunch of images and try to classify as just like type 1A, 1B from like a lot of data. And then also like spatial clustering of dark matter halos. So you can kind of make different clusters in your data. Yeah, and so in general, ML can be very useful in finding patterns we might miss, like weak signals. So stuff that the human eye can't really see, but the computer, since they're just processing the images as numbers, can detect more clearly. Okay, just here's some images from before. Yeah, so you can kind of see a lot of the machine learning and astrophysics examples also kind of tie in with computer vision and all of that, since you do have to do a lot of image processing too. Yeah, and so this was just a really quick intro. There's a lot more courses and other resources you can have look at to learn more. So here's like a link to a blog with a lot of other links. And then if you're really interested, you can try taking other classes in the data science and computer science departments, or you can also just look at their websites since they all have all of their course materials on it if you just want to take a quick look. Oh yeah, but now I'll do some fun demos. So.
Everybody, so this is going to kind of tie back to what we talked about last lecture, but it still, I think it better applies in the context of machine learning. So we're going to do like facial recognition software. So like on our own computer from my video, I can track my face and stuff. We're going to use a library called Opencv. We kind of mentioned it last time. And just so that we get a bit of context before I actually show you, I just want to like give a little explanation of what's going to happen. So there's already like a prepackaged model, aka a neural network. So a lot of like really complicated machine learning algorithms that classify things, that like classify whether or not this is a face or whether or not this is something else. Like there's a lot of parameters that go into that, and it's really complicated. So they use neural networks, like Emily was describing earlier, and they have like an image base of like hundreds of thousands of faces that they train it on to make sure it gets like as many, it sees as many examples of what a face is, where you tell it this is a face or not a face. And that model gets trained on some really big computer with lots of computational time over, hours, maybe months, weeks, who knows. And then you could save that like function, which it's basically just a function that like you would write in Python, like f of x returns x or x times whatever. But in this case, it's like a function that is like custom trained with a whole bunch of these little parameters. So like n1, 2, 3, 4, 5, 6, you could think of those as like little knobs that the function or that like the computer can twist to make sure that your function takes in an input and gives a correct output based on what you tell it is correct and wrong, or right and wrong. So they do that for you already, so you don't have to actually train it yourself. But the end result is like something that you could just send over to somebody, a model. You could put it on the internet, you can put it wherever you want and just start feeding it in data. So Emily was talking about the training and testing data. That's all just to make sure that your model works. But once it actually works, you can send it out into the real world. So an example of this would be using something called Opencv to do facial recognition. So I'll show you how to get this on your own computer so you can play around with it. But I'll just show you first how it works. So I'm going to take my mask off for this. But I just have like a little script called facedetect.py, which just has a bunch of code in it. It's like, I think maybe 15 lines or something, 10 lines of code, just using their like function that they wrote. And you can see there's like a green rectangle around my face. And it's in real time taking every image from my video, and it's looking for what a face looks like. And based on last time, what we talked about, like we talked about how like computer vision, you can use like different filters and convolutions with kernels and stuff like sharpening or Gaussian blurring to kind of help you detect features. So an example of something that might help a computer detect eyes or like a face, like a head, would be to sharpen the image so that you see like sharp, dark pixels around the face and maybe some in the eyes, and maybe it's like, for most humans, like the eyes have some sort of like distance relation to the rest of your face and head, and then there's a mouth and a nose and all that stuff. And it could real time track, and it can track multiple people. Like I don't want to unplug. So there's Emily, and then I would flip it around, but I don't want to unplug it on accident. But if you're curious, you can come up, or you can try it on your own computer. So really quickly, I want to. It's like, it doesn't know what to, I want to close out the window, but it's thinking I'm talking about doing it to Zoom. Here we go. Yeah, okay, there we go. It's good. So if you want to download this on your own computer, I'm going to just show them really quick about the GitHub. So you can go to, where's Safari? How do I go back? Oh, okay. Cool. So if you wanted to, you could just go to GitHub. This is also linked on like the previous slides from last week. If you go to if you go to my repo James11, or my profile James11222, you could find this face detection demo, and you could download it yourself by clicking on this green button that says code, copying and pasting this link right here, and then if you just go into your terminal and then just go to a directory that you want to be in. So right now we're on, if we go pwd, we're on Emily's desktop. I don't know if people can see that. Zoom in. We're on Emily's desktop. So you could just git clone and then, I gotta copy this link. You can git clone, copy this link right here. Git clone this. And then if I press enter, it already exists, so I'm not going to do it again. But once it downloads, you can go into the folder that's called face detection demo ls, and then there's this facedetect.py right here. This is the thing. So this is the file. So all you do is just run python facedetect.py, and then that would run. There's another demo in here if you want to like cartoonify an image. You can do that too. I'll let you test that on your own. The only package you need to install is, I believe it's called pip install. You have to pip install opencv-python, and that's the only library it depends on. So just do that first before you run the file, and it should just work, hopefully. If not, let me know and I can help you with that. But that's how you can get like your own facial recognition. You just have to let your terminal access your video camera, and then you can like detect people's faces and stuff in real time. It's kind of cool, kind of terrifying, but I thought that was a cool example of using neural networks to detect faces. Is there any questions about that? Okay, then if that's the case, then I will bring it back.
Okay, now Claire's going to share some machine learning that she uses in her research.
Yeah, so I mean the biggest takeaway from working with ML is that it's like a little bit terrifyingly easy to set up. Like it sounds really stupid because the math and the like process behind how it works can sometimes seem like a bit of a black box. But like if you want to get started playing with some ML stuff, it's like surprisingly easy to do. Look up like TensorFlow or Keras online. There's like a ton of documentation for these Python libraries. People already set this up. So like the thing I wanted to talk about was some research I did like a couple years ago that I'm still like dabbling with every so often, but it's like a pretty nice example of, like how you might use neural networks in like astronomy research and like what you can do with it with data that, like literally everything I used for this project is stuff that we've covered in this class. So I kind of just wanted to bring it up. It's like, hey, it's like a cool starting point, a cool thing. Even you guys can like try out and play with, whenever. It's really neat. So like the whole, and it also introduces you to a lot of like small details that are kind of important when you do neural networks, like things that, come up as you're playing with them and you're like, oh wait, this is kind of important, oops. But yeah, like the main gist of what I did, what this whole project is you've probably heard about it. It's like trying to detect like exoplanets with neural networks. You pull some data, you when like a planet moves in front of a star, like the light of the star dips a little bit, and we want to try looking for those events, right? If you just look at this data with your eyes, you might be like, wait a minute, that could be a transit, or maybe that, or maybe it could just be noise, or like the star has some activity, or it could just be dust or whatever, right? Like it's really easy to get false positives or even false negatives. This is what like actual exoplanet data looks like, right? And it's kind of hard to tell where some of the transits are. Like that top left one, the star is kind of like doing its own thing. It's got some activity. So it already looks kind of like, it's got oscillations. It's really hard to tell what's a real like event and what's not, right? And like was said earlier, this kind of thing is a great example where like using a neural network could be super helpful, because you as a person, examining this data, you might miss a lot of things, but the neural network can pick it up. And like it was said earlier, a large part of, like when you're setting up a neural network is how do you train this thing, right? Like what data do you give it? And of course, like you have to be kind of mindful of, what kind of features are you looking for in this data? In my case, I'm looking for those little dips, right? Those little like things that drop downwards, those transits. But you want to, make your training data such that it's as similar to real data as possible, but also encompassing a wide range of possible things that you might pick up, right? Like imagine if you're training a like neural network to detect faces, but the only training sets it had were of like, I don't know, white guys. Like that might not end up being a neural network that's great at detecting all kinds of faces, right? Like, broad example, but stuff like that. So you got to think about how you make your training data or what you pull it from, et cetera, et cetera. Training neural networks is hard. Data sets can be massive. You got to be smart about it. So like in my case with research, this research, there was like not that many confirmed actual exoplanets with the properties that we were looking for. So we ended up having to like use those properties to generate a bunch of fake transits and then chuck some randomness into them and chuck them into like actual data so that we could have something that simulates what kind of things you might want to detect. Because otherwise, like you're training the data set on like, 1,000 examples, which is not a lot. And you want to cover as wide of a range as possible. Literally what I did was I made some like trapezoids that were shaped similar to actual transits, chucked a bunch of random noise into them, multiplied them with like flat actual light curve data. And that's what all of these are. So like this here, the ones that are like blue highlighted are actual exoplanet transit data. The orange ones are ones we generated. And like we were trying to get to the point where the neural network would be able to detect like the positives from either. Oh my God, this is. So we talked earlier a little bit about like, you have like these different operations that your neural network is essentially doing, right? Like to your data to try to find specific features. This is what the actual code looks like for setting up the thing. You can kind of tell here, there's a bit of a flow chart. Each of these blocks there is like a different layer or a different operation that you're doing. So like you input this data, which is like a chunk of a light curve, right? It's got something in here. We want to see if you can find an event or not. There's one in there. And essentially it's like, how do you like break up this data, combine it, recombine it? How much of it do you keep? How much of it do you drop out to zoom in, on like a specific feature? How do you basically like bring that feature out? So essentially what all of these layers are doing is just, it's like bringing in stuff together to try to highlight features that you want it to highlight. But of course, like it's hard to tell at any point what exactly your neural network will be doing. It's just, how do you like set up these operations to, maximize its ability to find what you're looking for. So yeah, every so often here there's some like dropout layers, which is like, yeah, we chuck this part of the data. We look at this part, we like, pool everything back together. We look at it again. This was one of the first times we trained this neural network, and you can see it's kind of cursed. Like, we basically like train it and then we have it validate by seeing if, like it can actually detect what we're looking for when we put in like a testing data set. And you can notice that like the orange spikes there, that's all supposed to be like the validation accuracy, like how good it is at actually detecting something. And you can see it's kind of all over the place, which means that, yeah, maybe we didn't do a great job either like training it. There's some parameters we may need to tune a bit. It's kind of frustrating because you're like, well, okay, this is the data we're putting in. Maybe there's something wrong with that. Maybe it keeps like missing stuff. You can also look at something like this, which essentially it's a confusion matrix that essentially just tells you like how many false positives, true negatives, and false negatives your neural network picks up. Like how good is it actually at finding things? When you, at least like with the thing I did, when you train it and then you have it test on, a bunch of light curve data you feed in, it chucks out a bunch of stuff like this, which also does look kind of cursed. The top bar is like the events that it thinks it found. The bottom is basically how the probability of it picks up of like how likely it is that there's an event here. And you can see some of them, the original data might have been like super noisy or had a lot of other stuff going on, or even like other chances that we didn't filter out. So it like creates a lot of these things that you see as spikes here, where it's like, oh, maybe this is an actual event. Maybe that's an actual event. In that one on the left, oh, we think there's events everywhere because it seems like we found, like big dips in the light curve everywhere, and we think they all look legitimate. So we think all of these have a high probability of being real, when in reality, like that's probably not the case. You also have to deal with sometimes things that look like this one here, where it's like a bunch of peaks that seem to happen periodically, and you're like, wait a minute, is this real? Or maybe it's just harmonics. Maybe it's just multiples of something that already exists, whether it's like, noise or like another event that we didn't filter out, and it gets multiplied. So we have a bunch of things that look legit, but actually aren't. They're just like a, thing that got magnified when we fold it over and over. And then meanwhile, this one on the right here, the neural network thinks there's very clearly an event happening at like a 200-day period, and it picks that out, which seems like it did a decent job. But then like the problem, we looked at this, we were like, oh, okay, the problem ends up being the data we were training the neural network on was not the best. We were giving it just like a giant amount of random stuff. And like, you looking at something, you're like, this is a ton of information. I don't know where to start. I don't know how to pick out features. We also, like the neural network had the same issue where like, we weren't zoomed in enough on some feature. So yeah, we basically made this thing, we called it the Minesweeper algorithm, because it was essentially just, let's look for places where it seems like there's something going on. There's like some data that's several standard deviations away from, your baseline. And we'll just like cut there, pick that out, and like chuck it into the neural network. And the nice thing about that was it like cut down the amount of data the neural network was looking at by a bunch, and just limit it to the places where it was like, most likely that there was actually something important or interesting. So like on the left was what we were feeding it initially, and right is like after we, implemented this like sort of, we call it like sigma clipping or something stupid like that, but it's like basically a filter sort of to pick out like the things that we would most likely actually care about. Train again, definitely less cursed than initially. Like it's still not great, but this was like a few epochs in. I don't know if I have the like plot from the end, but like the validation losses ended up getting decently better. I need to find the actual thing, I don't have it, but yeah. And like right here again, like we train it, we test it, we validate, we put in a bunch of data and see if it can, like actually find the things we want it to find. And then after many cycles of just like, oh, let's try to make this data better. What's going on with the neural network? Why is the accuracy low? Oh, maybe it's this thing. And you keep iterating and revising. And then from like this data, we narrowed it down from initially spitting out like literally thousands of candidates to spitting out like 100. and we just went through and processed everything. There's this thing called Markov chain Monte Carlo methods, which are, it's like kind of annoying statistics, but worth looking into if you're interested in this kind of thing. So what you end up is like the neural network does most of the work for you. It picks out a bunch of like things that it found that might be significant, but you could hypothetically have it improve it to the point where it could even do vetting for you. But if it can't, that's where like it gets handed over to us. And we do a lot of statistical processing and whatnot to try to, like find the properties of these things that we might have found, see if they're statistically significant enough. Like, is this real or is this a false positive or a false, where it might have come from. You can see some of these plots here, they show like sort of the significance essentially of what you're looking at, and they look kind of funky, which means that either like something is off or our like fit is not great. But the fact that these are kind of oblong and could maybe be circles if you looked at it the right way means maybe we're on the right track. It's a lot of really just like guessing and tuning and then more tuning and then trying to see if you're going in the right direction to figure something out. But it's like some of the results. Yeah, you want it to look something like this, at least statistically wise. The distributions are at least more reasonable. But yeah, that's just might be a little bit of a mess. There's a lot of really just like small intricacies that come up when you're working with this kind of thing. I kind of just wanted to mention it as an example of like, how you might go about implementing a neural network for some kind of research that you might want to do, and just, a bit of a glimpse into the kind of pitfalls and frustrations and just like things that you might want to consider. It's a bit of a mess, but really like, yeah, I mean, just, yeah. A lot of the examples we went over earlier with, like pulling info from images, or you're trying to find like a, emission line in some spectra or whatever using neural networks. It's like, at least the way you would start approaching it is pretty similar, right? Like you figure out what you're looking for, what are sort of like the main features of that, and how to basically like get data to train your neural network on to find those things, and like and it helps really to know like the characteristics of those things that you're looking for, so you can be smart about it. Like there were some cases early on with working on this where the amount of training data we had was it was like such a large amount of data that it would either time out or like crash stuff when we tried to load it in. And we were like botched it together by writing a thing to load in the training data like piece by piece. And even then it was really stupid. So the solution we ended up having was like, wait, what if we were just like smarter about this and didn't load in these like big chunks of data and, broke it down into something smaller where we'd also be more likely to actually find stuff. But in summary, lots and lots and lots of fine tuning. It's a good tool. It's a very interesting tool, and there's a lot you can do with it. It's very powerful, but also definitely can be frustrating. But yeah, that's just a bit of a glimpse into, what you can do with stuff like this.
Yeah, so that's all we had for today. So thanks everyone for coming, but please stick around if you have any questions related to your final project. I also have office hours at 5, so feel free to come to those or any of the other office hours this week. But yeah, you guys can all go. Like that was it for today.